Hello and welcome to another episode of Literature Talk. Today we have with us Ramkrishna Misra. He completed his MSc from Vishwabharati University and he is currently a second year PG student at IISc Bangalore. In today's presentation, he'll be discussing an exciting and important area of research, blue organic light emitting diodes based on triplet annihilation. So Ramkrishna, welcome to the talk and the screen is yours.
Thank you, Bhai. Welcome everyone. Today I will be present about blue organic light emitting diode based on the triplet annihilation process. As we know that blue organic light emitting diode based displays everywhere nowadays, from your smartwatch to your smartphone, TV and many other electronic devices. And blue organic light emitting diodes is a crucial part of the OLED device technology. So before we going into the details on this topic, let us first look at the evolutions of display technology. We started from cathode ray tube display, then we moved into LCD with CCFL backlight display, followed by LCD with LED backlight display, and nowadays organic light emitting diode based display is represent the more recent generation display, where the emissive layer itself generates the light. Therefore, we don't need any backlight. OLED display give us the advantage like lower power consumptions, high flexibility, high color purity, and also suitable for the thin device architecture. Therefore, OLED device represent a competitive and the promising alternative for the full color next generation display technology. For a good full color display, we need three primary color emitters: red, blue, and green emitter. Due to the mixing of these three primary colors, we can produce almost the other colors. So when you talk about the color, it is important to define what we actually mean by these three primary colors. According to the International Commissions of Illuminations for ultra high dimensional display, the red color lies the CI coordinate value around 0.708 and 0.292, where the green color lies around 0.17 and 0.797. In this region, both the red and the green emitter nowadays commercially available with high color stability, high color purity and stability. But in the case of the blue emitter, which lies around 0.131 and 0.046 in CI coordinate value, the achieving the emissions in this region with high efficiency, color purity, and good stability is extremely challenging because the energy gap between the HOMO and LUMO in the case of the blue emitter is high compared to the red and green emitter. Here the energy gap in the case of the blue emitter is around 2.8 to 3.3 electron volt. And in this energy, most of the organic molecule and device itself chemically unstable. Still, we need good blue emitter to achieve the high color purity display. So now the naturally questions arises how to achieve the high performance blue organic emitter which have both the color purity as well as good stability. So before we going into this talk, before we addressing these questions, let us look at the fundamental difference between the photoluminescence and electroluminescence. In photoluminescence, at first molecule absorbs the photon and it's excited to the singlet excited state. It cannot directly excited to the triplet state according to the spin selection rule. Triplet state is only populated via inter-system crossing process. And when the molecule coming back to the ground state from singlet excited state, it emits the light as a fluorescence. And when the molecule coming back to the ground state from triplet state, it emits the light as a phosphorescence. And in the case of the electroluminescence, after applying voltage on a device, hole and electron are generated and they recombined and form excitons. And according to the spin statistics, 25% of the singlet excitons 25% of excitons converted into singlet state and 75% of excitons converted into triplet state. And when the singlet excitons coming back to ground state, it emits the light as a fluorescence. When the triplet excitons coming back to ground state, it emits the light as a phosphorescence. Here, in the case of the electroluminescence, triplet state is more populated compared to the photoluminescence. And OLED device based on electroluminescence principle. Therefore, we only focus on electroluminescence. In electroluminescence, How the excitons are utilized based on this, the organic emitter are classified into several generations. In first generation, which based on the fluorescence material, here the 25% singlet excitons utilized to generate light. And the rest of the 75% tablet excitons, they coming back to ground state via non-radiative process. Therefore, maximum reach up to 25%. And maximum external quantum efficiency reach up to 5%. Due to this inefficiency, the second generation emitter, which based on the phosphorescence material, has been explored, where the singlet excitons converted into tablet excitons via intersystem crossing process. And most of the phosphorescence molecule, they contain the heavy metal or heavy atom, which enhance the intersystem crossing process. Therefore, the maximum internal quantum efficiency reach up to 100% and external quantum efficiency reach up to 20%. But the problem is here, the energy gap between the T1 and S0 is too low, which is not suitable for the blue light emissions. To overcome this problem, the third generation emitter, which based on the thermally activated delay fluorescence, has been explored, where the tablet exciton converted into singlet excitons through the reverse intersystem crossing process. And also here the internal quantum efficiency reach up to 100% and maximum external quantum efficiency reach up to 20%. But the problem is here, the most of the TADF molecule, they emit the light in greenish blue region, not in the copper deep blue region. And also the designing of the TADF molecule is not too easy because the energy gap between the T1 and S1 state is too low, around 0.02 electron volt. Therefore, the 2.5 generations emitter, which based on the tablet annihilation process, has been explored. When at first two tablet states they come to close proximity and they interact to each other. After that, they exchange their energy, and one of them is going to the singlet excited state, another one is coming back to the singlet ground state. When the singlet excited state molecule coming back to the ground state, it emits the light. And in this process, the partially tablet harvesting is possible without using any heavy metal atom. And this one is also suitable for the blue light emission because now the energy gap is increased. And here the external quantum efficiency reach up to 12.5%. So how these processes actually work, to understand this process, we need to understand its mechanism. According to the mechanistic part, triplet annihilation is classified into two categories. One is optically pumped TTA process, another one is electrically pumped TTA process. In the case of optically pumped TTA process, at first sensitizer or donor molecule absorbs the photon and it's excited to the singlet excited state. After that, via intersystem crossing process, sensitizer tablet state is populated, which is long-lived tablet state. And this sensitizer tablet state transfers its energy to the annihilator molecule through the tablet energy exchange process, and now the annihilator tablet state is populated. And when the two annihilated tablet states coming to close proximity, they exchange their energy and at first form one singlet intermediate. After that, this singlet intermediate converted into one singlet excited state, another one is singlet ground state. And when the singlet excited state molecule coming back to ground state, it emits the light as a photoluminescence. Now the two processes involved. First one is tablet energy exchange process. In tablet energy exchange process, at first higher energy electron of sensitizer transfer into the LUMO of the annihilator molecule. At the same time, the HOMO electron transfer into the sensitizer HOMO. Therefore, sensitizer tablet state converted into sensitizer singlet ground state and annihilator singlet ground state converted into annihilator tablet state. And when the two annihilated tablet states, they coming to close proximity, they exchange their electron via Dexter electron transfer process and they form one singlet ground state, another one is singlet excited state. This process known as a tablet annihilation process. Now the second one is the electrically pumped TTA process. Again, it's classified into two categories. One is direct electrically pumped TTA, another one is electrically pumped TTA via sensitizer. In the case of direct electrically pumped TTA process, after the applying voltage on device, the hole and electron are generated and they recombined and formed excitons. And according to the spin statistics, 25% excitons converted into singlet state and 75% excitons converted into triplet state. When singlet excitons coming back to ground state, it emits the light as a pumped electroluminescence. This process is a spontaneous process. After that, when the two triplet states coming to close proximity, they exchange their energy and at first form one singlet intermediate. Then this singlet intermediate converted into one singlet excited state, another one is singlet ground state. When the singlet exciton is coming back to ground state, it emit the light as a delay electroluminescence. On the other hand, in the case of the electrically pumped TTA process via sensitizer, here after the applying voltage, the sensitizer triplet state is populated. And this sensitizer triplet state transferred energy to the annihilator molecule via triplet energy exchange process. And now the annihilator molecule is populated. And when the two annihilator molecules they interact to each other, they at first form one singlet intermediate. After that, this singlet intermediate converted into one singlet ground state, another one is singlet excited state. And when the singlet excited molecule coming back to ground state, it emits the light as a delay electroluminescence. So there is a several classical criteria to design a triplet annihilator molecule. The first molecule should have shorter singlet lifetime, which enhance the fluorescence rate. Second one is the molecule should have longer triplet lifetime with increasing the probability between the two triplet state interactions. And the energy criteria is the first triplet twice of the first triplet state energy should be higher than of the first singlet state energy, and twice of the first triplet state energy should be lower than of the first quintet state energy, as well as should be lower than of the second triplet state energy. Here we see one general OLED device architecture. Generally, OLED device made by several organic layers sandwiched between two electrodes. Here, the emissive layer is connected to the hole transporting layer and electron transporting layer. And anode is connected to the hole injection layer followed by hole transporting layer. And these two organic layers helps to transport hole into the emissive layer. On the other hand, in cathode is connected to the electron injection layer and electron transporting layer. And these two organic layers helps to transport electron into the emissive layer. And in emissive layer, hole and electron are coming and they recombine and form the excitons. And when excitons relax to the ground state, it emits the light. Now, there is several examples which demonstrate the blue emission based on the triplet annihilation process. Due to time limit, here I show only few class of molecule. And most of the TATA triplet annihilator molecule based on the anthracene molecule. Because anthracenes come with its unique interionic interelectronic properties like high photoluminescence quantum yield, wide energy band gap, and also good thermal stability. Therefore, the Lie group they synthesize these three cyanoanthracene based sterically hindered molecules. After that, they study their photophysical properties and they got photophysical properties and got the high luminescence deep blue emissions in DCM at around 440 nanometer. But while in solid state, the emissions were redshifted around 450 nanometer. After that, they made the non-dop OLED device where they use these three molecules as a emitter or emissive layer, but it is important to understand that they are not use these three molecules together. They use one molecule in one device. Therefore, here they made total three devices using the three different emissive layer. And they study their electroluminescence properties and got the deep blue emissions around 443 to 447 nanometer with good external quantum efficiency value. After that, Wang and co-worker, they synthesized these two bipolar molecules where they introduce one carbazole molecule into cyanoanthracene skeleton. After that, they study their photophysical properties and they got the deep blue emissions in both cases in DCM, means solution phase, and also in solid phase. Therefore, they made a non-doped OLED device and they record their electroluminescence properties where they got the deep blue emissions for the both devices. Here, the here the first device is based on the three carbazole based molecule. They go in this device they got the external quantum efficiency around 10.06%, and CI coordinate value of the emissive light is 0.14 and 0.14. On the other end, for the para-carbazole based molecule, they got the external quantum efficiency value 9.23 and CI coordinate value is 0.14 and 0.1 for the emissive light. Here we see the external quantum efficiency is good, but the emissive light color purity is not good. They are generally comes with greenish blue to blue region, not in deep blue region. Now this is the another type of triplet annihilation emitter where they use the heterocycle molecule in anthracene skeleton. The loop group, they synthesize these three nitrogen heterocycle based nitrogen heterocycle anthracene based molecule where they use donor acceptor based molecule. And all of these three molecules, their emissions in blue region in the both case in solid state and also in solution state, around 461 to 482 nanometer. Therefore, they made the OLED device by using these three molecules as a emitter, and they got the blue emissions for all the devices around 464 to 484 nanometer with good external quantum efficiency value. And not only the anthracene molecule, also pyridine-based molecules show the triplet annihilation process. Therefore, the Chang group, they synthesize these three pyridine-based molecules. After that, they study their photophysical properties and they got the deep blue emissions in solid state. Therefore, they made a non-doped OLED device where they using these three molecules as a emitter, and they got for the device D where they use the PCZSP molecule, they got the deep blue emissions compared to the other two device. They are generally slightly red shifted, and for the device F, they got the high external quantum efficiency compared to the other two devices. Now, triplet annihilations give us the promising alternative to blue light emissions, but it has some limitations. First, the maximum external quantum efficiency reach up to 12.5%, and color purity is not optimal. So, how to overcome this problem? To increase the external quantum efficiency, we need to increase the outcoupling efficiency of the device. What is the outcoupling efficiency of device? How much light is actually emit from the device? It's known as the outcoupling efficiency of that device. So generally, for isotopic arrangement of the molecule, the outcoupling efficiency reach up to 20%. And as we know, the emission is always occur from the perpendicular of the dipole of molecule. Therefore, if we arrange our molecule in horizontal arrangement, that time we will get the outcoupling efficiency up to 45%. And to increase the color purity, we need narrow band emissions, because in broadband emissions, the color mixing probabilities increases. As we see here, the blue light mixed with greenish blue region and also some purple color. Therefore, color purity decreases. But in narrow band emissions, the color mixing probability is minimized. So how to achieve this narrow band emissions in molecule? To achieve the narrow band emissions in molecule should have locally excited state, rigid and planar structure. Now, so what we see, the triplet annihilation process give us the alternative approach to generate the blue light emissions with a good external quantum efficiency, but it's not fulfill the future stability issue. Therefore, the other emissive layer, like the magnetic resonance, TADF OLED emitter, hot excitons fluorescence based emitter, and hyperfluorescence based emitter, and also quantum dot OLED based emitter being extremely sturdy because they provide narrow band emission. So now I summarize my talk. At first I discuss why the blue emitter are challenging. After that I introduce the concept of triplet annihilation process. Therefore I show some molecular system and device performance is reported in paper, and last the further improvement and the future perspective of the blue light emission based on the TTA emitter. Thank you.
Nice presentation, Ramkrishna.
Thank you, Bhaiya.
If you enjoyed this session, don't forget to like, share and subscribe. We'll meet you in the next episode, next session. Thanks for watching.